at the Astronomisches Recheninstitut in Heidelberg, which maybe some of you know. It's a very renowned institute in the context of fundamental astronomy. Michael has been involved in Gaia since its very beginning, and actually he has already been involved in the predecessor, or the planned predecessor, which was the DIVA mission, which was originally a German mission only, which then later gave important input into the Gaia mission, which, I think you really said it, revolutionizes what we know about our galaxy, but not only, but also about stars and the cosmos in a very general way, because whenever you do some analysis involving the properties of a stars, the fundamental properties is where you start. And this is what Gaia is giving us. Gaia is, as you probably know, the successor of the Hipparcos mission, which was back in the 90s, or I think in the 90s, yes. And now Gaia has taken it, of course, on a completely different level. Now you are at full stream in the analysis, and there are these different releases. I guess you are very busy, so we are particularly happy that
all the time, yes.
Yes, that you are here. Michael got his PhD in 2001, also in Heidelberg. Heidelberg is a very nice city, so if you have not visited it, I can recommend it. You can go there and also look at the nice building where the army is located. Okay. I don't want to wait any longer. Please, Michael, go.
Many thanks, Christoph, for the nice introduction. Good evening. It's a great pleasure to be invited to tell you about ESA's astrometry space mission Gaia, which is providing the most accurate catalogue of stars and objects in the Milky Way and beyond. And that doesn't work, so I do it some way. Good starting point. Yeah. Okay, finally it works. So why was Gaia set into life? The main goal of Gaia is to help us to better understand our galaxy, to see which structures build our galaxy, which components are there, what kinematics drive these structures, how they come together in terms of forces and movements, how everything is connected. And the ultimate goal of that is to finally piece together a picture of a coherent formation history of the Milky Way, so that we really understand how it has been built, how it has come to life, and why it's looking the way it's looking now. That is kind of the major thing people had in mind when they started thinking about when to do Gaia. And by the way, the history of Gaia goes back into the 1990s. So I didn't start at that time. I was there when the consortium was built, but the idea for Hipparcos is more than 30 years old already. What we also want to do, and that Christoph already mentioned, is to understand physics of stars a lot better with the high accuracy data we get from Gaia, and to enable also many other advances in almost practically every field in astronomy. There's practically no field in astronomy which has not already benefited from Gaia, which I will discuss later in some more detail. So Gaia was launched in 2013. We had a quite extensive commissioning period to get to know our instrument, our satellite, how it really works, that we have a rough idea of the calibration, which we would then of course improve over time. And since 2014, July, we are in operations, and ever since then we are observing stars and other objects in the sky every second. We had 3 releases so far. The very first one is kind of not really a release for us working on Gaia. That was in 2016, it's just a teaser, just a sign of we are alive, we are there, we do something with the Gaia data. The first real Gaia release was DR2 in 2018, and then there was a third release in 2 stages, 2020, astrometry and photometry, and all the rest of the information 1 year later in 2021. 2 more releases will come. The next one is for the first half of 26, and then the final release is 2030 or maybe later, depending on how quickly we go through the data and really process all it. A lot of things come out of these. That is why I have this view graph a bit longer, so that you can appreciate what's coming out. With the third release, we have published data for 1.8 billion sources. 1.5 billion sources come with astrometry. Astrometry is the positions of the stars, the distance to the star, and the motion on the sky, so the proper motions, plus the magnitude of the star. There's a lot of extra information for less sources than going down to RVS information, so the radial velocities for at least 33 million sources, which is also one of the biggest, no, the biggest catalogue in this respect, although it's small compared to what Gaia does. It's many more things than are presented here. It's also 1.3 million quasars we have identified in the Gaia data, plus. So there's a lot more, but I will mainly focus on things that are presented here. And Gaia is observing every source it sees which is brighter than a limiting magnitude, which is 20.7 magnitude, and that is the light you get from a candle in 30,000 kilometer distance. So it's rather faint, all this you observe. That is why we get the high number. Gaia data has many advantages for what I will later present in terms of science. One thing is that it's full sky with one single instrument, or a few instruments, one for astrometry, one for photometry, and one for spectroscopy. It's highly accurate, what we produce. Highly accurate, to just give you an idea, if the typical positional accuracy is the angular distance here of that USB stick, if you would be Gaia and this USB stick would be on the moon. So that is a typical uncertainty in position we have for the objects we publish. What Gaia really makes unique is distance. And why is distance so important? If you don't know the distance to an object, you have no idea of the true size of that object you're observing, and you have no idea of the true amount of energy released per second of that object. The only thing you see is an apparent magnitude, size of that object, which is of course distance dependent. And what you also get is the apparent magnitude of the star, which is also magnitude dependent. So if you really want to understand the physics of the object you are dealing with, you really need to know how distant they are. And that is what really makes Gaia unique, because for almost every source we observe, we compute a distance. That was a 1.5 billion out of 1.8. And we will improve on this in the future, of course. So how do we do this? You all know this by heart, because you do it all the time yourself. Maybe you don't realize this, but there's a good reason why you have two eyes. The second one is not a backup in case the other one breaks. It's if you observe objects, you see it from slightly different angles, with the two eyes separated in your face. And you see it from in slightly different angles compared to the background. And this angle, from one eye to the other, the shift relative to the background. This gives you an indication on how far or how close objects are. It's the very same we are doing with Gaia. Gaia is flying with the Earth around the Sun. So seen from the Earth, seen from the Sun, flying behind the Earth. It's going around in the yearly orbit with the Sun around the Sun. And so it's observing stars from different angles, separated by 300 million kilometers. So these eyes are really far away, really strongly separated. And these little elliptical movement of stars, just the projection of the Earth's orbit onto the sky. That is what we observe. And this way we compute distances. The smaller that ellipsoid movement is, the farther away is the star, and the larger it is, the closer it is. And of course, in real life, it's not just this parallax motion of the star, which is just caused by the movement of the Earth around the Sun. Stars themselves move, and that is they just pull apart this ellipse by a spiral. Yeah? And for these signatures, we look with validating. We have typically a few hundred observations per star, and that is enough to really compute these distances in a very accurate way. That also should give you kind of an idea of what we are doing. This tiny yellow dot here, that is where Hipparchus measured stars, 120,000 in our Milky Way. And already from this tiny area, we could clearly see that our galaxy is a spiral galaxy, because that barred spiral galaxy, because that bar in the center of the Milky Way has influence on the movements of stars far outside, because it changes the potential in which the stars move, and that we could see in this tiny yellow dot already. Now with DR1, which I don't regard as really Gaia release, we have increased this dramatically, and this now is the area of the Milky Way we are really observing with Gaia every day. This will not increase a lot in terms of size, but of course it will improve a lot in terms of accuracy. I will soon stop the discussion about Gaia and go to the more interesting science, I believe. But one thing I still would like to tell you, Gaia has 2 viewing directions. That is the only way to do really absolute astrometry, so that you don't rely on any other source of information, can do astrometry just yourself. It has 2 viewing directions, it's rotating all the time, 6 hours, it needs to just rotate once, and then the axis of the rotation is just processing with time, so that over time you just scan over the whole sky. And while you scan over the whole sky, stars just enter here on one of these 2 CCD rows. One is just for one viewing direction, the other is for the second viewing direction. Here is clearly seen by the different colors, or indicated by the different colors. And for the rest, our really needed information for the astro instrument comes from, or they are put together, but we know which star was in which viewing direction because that was decided here. And then we also have photometry and spectroscopy later on. You typically have 300 observations per second, and then you just can get a rough idea how many stuff that is. If you can't compute it yourself in quick time, we have more than 2 or almost 2.5 trillion astrometric measurements done so far. That is from today, these numbers. So that is quite something, and that is what makes our data product so precise, because we have just an enormous amount of data. One thing that I believe I should make clear, if you really want to have this accuracy for stars, you have to do something to get it. You just cannot simply observe and hope everything works. So with the same position, we want the positions of the catalogue to have. We need to know where Gaia really is in the solar system. And we need to pin it down to the level of 30 meters at every moment in time, compared to 30 meters to 300 billion meters for the orbit. So that is quite precise at any time. We also need to know the velocity of Gaia at any time down to 2 millimeters per second, just from all the observations we do. Again, this is compared to 30 million millimeters per second, which is the velocity of the orbit, the Earth's orbit. So these things we have to get out of the data itself. We also need to calibrate the optics, the detectors, where the CCDs really are located down to this level. And we also have to take into account relativity, because every larger body in the solar system bends light, and if we don't take this into account, we see the star at the wrong place. So we need to know this. Which also means that we need to know the positions of the larger bodies in the solar system down to 30 meters accuracy, which wasn't available before Gaia, and it's kind of a side product of our data processing. What I'm presenting today is not my work, not at all. I'm just one person out of about 450, which are spread over 160 institutes in Europe and ISSI, and there's many big data centers just processing the data kind of all the time. They are kind of never in a relaxed phase, these processing centers, because it's just a lot of data, and we have to test and test and test before we do a release. And what you see here is just 1/3 of the group, which is producing all these just fantastic data. You can all download yourself. It's not just for scientists, it's for everybody. Everybody can use the science data. So I've talked a lot about Gaia, but let's do science now, which is a bit difficult if I really would want to give you an overview of what Gaia really does. Because it's really an all-purpose instrument, a general-purpose instrument, and there's practically no field in astronomy where you cannot benefit from Gaia data. And you can easily see this by 11,500 papers which have been based on Gaia data published since 2013, which is several per day. Working days, it's almost 10. So this is an enormous amount, no chance to read it, and I just give a very tiny insight of a small fraction of what can be done with Gaia data. Let's start with something which is more related to stars. That is a Hertzsprung-Russell diagram, which you see here. Astronomers just put stars into a diagram which gives the absolute magnitude, that is the magnitude this source would have in a certain distance, 10 parsec, and compare it to its color, which is related to the magnitude, to the temperature. So that here is hot, and that is cold. And what we see is that stars don't spread evenly in this diagram. There is structure in, and the main structure here that you see, that is what we call the main sequence. This here, that is where stars live most of their time. So they are just born, and then they just burn hydrogen and live for, if they are really massive, for 10 million years. If they are like the sun, it's 10 billion years. And they live most of the time here, and at the end of their life, just go up here and finally fall down here into the sequence of white dwarfs, which is an end product of star formation for the not so massive stars, like our sun, that will also finally end up there. And I would like to dive into this a little bit more. You can see tons of structure in this plot, which people know it should be there already before Gaia, because from a theoretical point of view it was clear that there's a lot of structure in there, but for the very first time we really see it. And just to compare, there was the Parker's predecessor for Gaia. Of course, we had also this kind of diagram from that mission, and you clearly see that there's almost, compared to nowadays, no structure. You don't see the many features, which I will dive into now. So let's just zoom into the sequence for the white dwarfs. And probably you already see it, there is some overdensity here. This dark area here. Dark means it's more sources in. And what you see here is those white dwarfs which in the outer shell have a lot of hydrogen. The point here is, no surprise that these white dwarfs exist, but now we can finger point. I know who is it. I can just pick them up, and I'm interested in those. There's a second dark area here. That is the white dwarfs which have helium in their envelope, in their shell. And then you see, not so much pronounced, but you hopefully see it, there's an overdensity here. That was long predicted, that is a certain state of white dwarfs when their core really becomes crystalline CO. So they have really crystallization in their very center of the core, that is a specific situations white dwarfs come in, and also those we now know. We can better really prove our theory, our models, by really observing exactly those white dwarfs which we know that they are in that stage. The next thing is, I have to check which the next one is. No, that was the wrong direction. Yeah, you have seen maybe an overdensity here. Not very much pronounced because it's fewer sources, but this is white dwarfs in double stars. And not just double stars, but double stars of two white dwarfs. Of course, you can also have double stars with white dwarfs and normal stars. And also those we know, in wrong region, that is those which lie between the white dwarf sequence and the main sequence, which is over here. And And I believe, yeah, that's it for the white dwarfs. So let's do something else with stars. When we plotted such an Ashburn-Russell diagram, people realized that there is a very tiny gap here. This is really very tiny. It's something like 20 millimagnitudes of the order, but clearly visible in the data. And also this was not so much at the end a big surprise to find it. Well, it was a surprise to find it, that the data is accurate enough to see it, but it was seen. What is the idea here, that is two stages of stellar evolution. So what usually happens in stars, in their very core, energy is transported via radiation, because it's too dense, and then in the outer shell of the star, then it's transported via convection. And there's a special stage in stellar evolution, exactly at that area, where the star becomes fully, where there's no radiation in the core, but just convection, sorry, yes, for the whole star. Yeah? And that is exactly this transition between the two. Where the magnitude of the star does a little jump. And we see that. Different topic. Now it comes to kinematics. What we have observed with Gaia is that there are a few stars whose velocities within the Milky Way are extremely high. They are going up to more than 1,000 kilometers per second, which is quite untypical. And if they would have had this velocity since their birth, they would no longer be in the Milky Way. The Milky Way is not big enough for that velocities to keep the sources. Yeah. So they must have been created. The velocity of that star must have been built in some way. As usually, if these things are detected, theoreticians just love to jump onto this. They want to understand where it comes from. And the idea was, could it be that there is, again, a double star? And two stars are observing. One is evolving quicker than the other. And this one evolves into a white dwarf. Then the second one is evolving. And the two stars come close together. And from the envelope of the second evolving star, all the material flows onto the white dwarf. It becomes too heavy to become stable or to stay stable, and it just explodes. Now that the partner of the new one, of the new star, which is still in its evolving phase, is gone. There's no reason for that star to orbit something which does no longer exist. So it flies away with the velocity it has at the time when its partner exploded. And because this is an evolving system, and the idea was that they are so close to each other that mass transport from one star to the second star could just happen, the orbital velocity of that surviving object is extremely high, and once the one is exploded, the partner, it just flies away. And that is the idea behind. Can we prove this? Of course, otherwise I wouldn't discuss it. What we see from Gaia data is what is the velocity and the direction of the movement of that star, and we just can predict it back where it was when in the past. And then we just observed, was there in that area, when it was just transported back in time, is there a supernova remnant? And yes, it is. That is this white area. That is the uncertainty for the placement of the supernova. That is our star, much increased in brightness, so that you just can see it. Now you see it moving in the direction it moves, based on the Gaia data. What we also can do is, and you can already imagine what happens. You can just push it back, see what it does in the past, and it just enters that area of where we know that the supernova is at the right time. The supernova remnant is not from Gaia data. That is why the uncertainty in the position is so large. Also, the time is of course not so precise, but it nicely fits. Nicely fits. It well speaks in favor of that idea. So very different topic again, structures in our Milky Way. Our Milky Way is built from many smaller structures, which we call clusters. And how do we find these clusters? We have roughly 2 billion sources. If you look into 2 billion sources, you don't see anything. It's by far too much to see something. But what you could do is just to slide the whole area, the whole distance you're observing into individual slices and observe the distribution of stars within that slices going to larger and larger distances. And then you just see them popping up. Here are 2. So you can easily, in an automated way, just find clusters of stars and flows of stars in our Milky Way by just doing step by step in a distance, letters, so to speak, going through the Milky Way and just finding them. And this was done, and a lot of them were found this way. So the easy part is done, getting to more complicated, but of course then also more interesting things. What we, our colleagues, found, when I talk about we, I do the science community, I'm not talking about myself. I'm not doing science with the Gaia, I'm producing the data with the science can be done. But colleagues of us found something very interesting. Think about a star which is going around the center of the Milky Way. These stars are not really in just planar movement, they just go up and down while they move around the Milky Way. So that is shown here. What these people now have done, they have on this plot here, which as a function of the height above or below the Milky Way plane, just put in here the velocity with which they go up or down. And they found this spiral. And this was quite a surprise to see the spiral, and I would like to tell you where the spiral comes from. The idea is that this is a sign of disturbance of the Milky Way by another Milky Way, just merged with the Milky Way. Quite some time ago, quite some time is well, something between 300 and 900 million years, probably at 500 million years or so. Rather massive one, and it just fall into the Milky Way and just disturb the motion of the stars in a way that this diagram produced a spiral. So why a spiral? Need to explain this first, and then you hopefully will see that this all comes along. So that at a given distance from the galactic center, you have one single star, to start simple, and it starts at height 0, so perfectly in the plane of the Milky Way. And we will see how this one evolves. I kick him out, let him fall down, and so he moves up and down while he goes around the Milky Way. That is the very same plot, but I replaced the distance to the center of the Milky Way by time. So what this one does, it goes up, it goes down, it goes up, continues to do so while he orbits the center of the Milky Way. And this one is now the plot we are interested in. That is again the height above this or below, and that is the velocity. And at the starting point, here is at z equals 0, so in the plane of the Milky Way, and here's the highest velocity going up or down. So I let them just move, and that is what happens. It goes up and down. You can also see this here, and the velocity goes up if he goes through the plane, and it's minimum if he's at the maximum or minimum point, and vice versa. So, okay, with one star you cannot do a spiral, obviously, so let's do more stars. And let's do the very same. They all go up at different amplitudes and go down at different amplitudes, but all in a very coherent phase, not disturbed at all, and obviously no spiral. That is what people kind of expected. So final plot, same setup, but I disturb everything, so all the stars now go down and up with different speed, different times, so they are not in sync, they just go in a chaotic way up and down, and that is immediately where you can build a spiral. So something that was very homogenized in the past was at some time disturbed by something massive, so that all the stars just in a chaotic way move around the center of the galaxy. And this kind of, again, is the same plot we saw all the time. That is now a simulation of this Sagittarius galaxy, that is our Milky Way. And whenever it comes close, you see that there's more disturbance in the orbits of the stars, which builds a spiral in this specific diagram. So from observing the Gaia, from letting Gaia observe the stars in our Milky Way, we can just see that there was this Sagittarius galaxy, which we even found. I hope you can see it. There's some slight bright overdensity here, and that is indeed the Sagittarius dwarf galaxy, which is still not completely merged with the galaxy, still orbiting it, but losing more and more mass, and at the end, we will not see it again. Well, yes, because everything takes time in astronomy. Finally, it will just disappear. That is one merger. There was another one, also possible because Gaia just observed 7 million stars, where we had the position on the sky, the distance to it, and full 3D velocities. So we really could determine the orbits of these 7 million stars. We had all the element abundances, so the chemistry of the sources. And we saw that they did not match in terms of orbit, in terms of the element abundances, the typical star which just orbits in the Milky Way plane. Yeah, so they come from different directions, they have a different metallicity abundance. So that's very clear that they all belong together, that they come from something different, and that was called at the end the Gaia, Sausage, and Enceladus galaxy. There were different groups. One called it Sausage because they really observe how the stars are just orientated. It looks like a sausage. Others called it, and that story are really nice. That is a colleague of mine also working for Gaia. She came to the name Enceladus because, according to the legend, Enceladus was buried under Mount Etna in Sicily, responsible for local earthquakes. And similarly, the stars of the Gaia and Enceladus were deeply buried in the Gaia data, and they have shapen the Milky Way, leading to the formation of its sixth disk. I will explain now why we really see that this merger made the galaxy, the Milky Way we are living in, with all the features you see there. To do so, just checking what the time says. Okay. I have to tell you a little story. That story was not made by my colleagues working on the Gaia project. That is a long theoretical idea of how our Milky Way has formed. And the nice thing with Gaia now is that we really can, with the Gaia data at hand, with this precise data, support this idea in a very nice way. It's not a proof, but it is a lot clearer that this idea really is how the Milky Way evolved. So how is that going on? In the very, very early days of Gaia, of the Milky Way, but it was not yet built. You have different clouds of gas at the very beginning, which see where they are more dense, where the clouds are more massive, see kind of a potential well which they fall in, so they come closer to each other, they merge with each other, and build the very first proto-galaxy, which finally build our Milky Way. This proto-galaxy is very chaotic. The stars which build in there have very chaotic, isotopic orbits. There is nothing like a disk at that moment. But after some time, there is quite some mass into this area, and then, not equally, but a really massive second merger comes. And this second merger may also come with stars, but at least with gas, but more important, with quite some angular momentum. And this angular momentum, with the proto-galaxy it falls into, just starts to create then a disk-like structure. Now, this momentum is conserved, and then the proto-galaxy starts to build a thin disk. This thin disk was oriented in some way, we don't know, and I don't think we will find out in the near future, but this was oriented in some way, but probably not at all in the way the Milky Way is oriented, like we see it now. What happened then is that a massive merger came. That is the Gaia, Sausage, and Enceladus, which I will hopefully convince you at the end that we really see it, that this one was the one who produced our Milky Way. And what is this one doing? It just hits the Milky Way. It was relatively massive, about 25% of the mass the Milky Way at that time had. So it's not as massive, but comparable. And two things happened then. So all the stars and all the potential, the gravitational potential of the merger changed the potential the stars in the Milky Way orbit in. And this is what caused that the old, rather thin disk in the Milky Way just tilted. It was torqued. It got a different orientation. And it was what we call colometrically hot, which means that you disturb the orbits of the stars, where they were formerly in disk orbiting. They got all disturbed and they go in more widely distributed directions. That happened to the stars, but also something happened to the gas. The gas usually comes a little bit later, and the gas cannot penetrate the gas of the protogalaxy, while stars can. Stars can just fly through stars, because the space is for stars totally empty, for gas it's not. So the incoming gas of the merger was just hit and stuck at the level of the gas in the Milky Way, and this oriented also according in line with the stars. So there was a new level of fresh gas coming in, and from that new stars were born, and that created a young, kinematically old disk, because all the gas is in the disk, and all the stars built from that gas are also in the disk, and they just orbit in a disk. So that was an idea that people had in astronomy. There were some indications that it should be right, based on if things go wrong, a few thousand observations, sometimes just a handful of observations, and that we changed this Gaia dramatically. So we took 10 million red giant stars, for which we all have good astrometry, so 6D information, full three-dimensional orbits and velocities. We have metallicity and alpha abundances. Alpha abundances are the abundances of alpha elements, and these are the elements which are produced mainly in supernova 2 explosions. So if a massive star gets to the end of its life, he explodes, and all the material then from the explosion that goes into the gas in the environment, that is the alpha elements. What we also have for these stars is the angular momentum for each of these 10 million sources. And we put it into something which is indicated here. That is the real azimuthal angular momentum relative to one this star would have if it would orbit on a perfectly circular orbit. So it's +1 if it's just moving like all the stars in the Milky Way, -1 if it's in the plane but orbiting in the opposite direction. And what people then saw is this picture. So what they do here is exactly this quantity which I just now explained as a function of the metallicity. So metal poor is on the left and metal rich is on the right side. And they found these plot here, which kind of clearly indicates that there are 3 phases. One is here, one is over here, and then this thing here. And this is indeed all what supports what I just now explained, and I would like to go through this. To make things a little bit more complicated, none of these things unfortunately come so easy. We have to talk about high and low alpha disks and structures. What is that? High alpha or low alpha is in reality is a short term for the alpha abundance relative to the iron abundance. So why is that something important to keep in mind? That is in connection with stellar evolution. As I said, supernova 2 produce a lot of alpha elements, but the iron they produce stays in their core. So it is not distributed in gas. It's hidden, so to speak. It's not available for the next star generation. This only comes into play when the second supernova type explosion happens, that is supernova 1A, that is when white dwarfs become or get so much extra mass that they explode. And if they explode, they totally explode, even the core of them, And in the last 10 seconds or so, they kind of burn everything down to iron, and then the whole mass of white dwarfs with iron at the end kind of and is available for the next generation of stars. So this means that high alpha usually is young disk, yeah, from the material stars were born, while low alpha is an old disk, from the point again of the material stars are born. They have a lot of iron already in. So let's find all the things I've discussed. On the left-hand side, we see the protogalaxy, that chaotic isotropic thing that is dominated by stars, as you see, which have kind of minimal net rotation, almost zero, which means that they have not built a disk yet. What you also can see is it's not entirely isotropic. This yellowish area goes more up than it goes down, so there is a net angular momentum in there, a net rotation, which is a sign for this early disk that was built, which is not clearly visible in, but where it comes from. And we will later see that they also contain objects. We really can see them from the merger, from the Gaia sources and Enceladus. What we really see is that is the metal poor part. It's really isolated. We really see that. It's not a disk-like structure like the rest of the sources, which are metal rich. So it's really isolated at the core of our Milky Way. You see that. We can see this even a little bit better. I very shortly go through that. That is another set of stars which also help us to see this. This is really, really old stars. You can't see this nicely here, but this is just because there's so much dust, and you see all the dust features. This cloud here has taken away all the observations here, but it looks really condensed, concentrated. And that you can also see here, that is a plot of the parallax, which is, at least for good parallaxes, the inverse of the distance. So it goes down from something which is a kiloparsec, 1,000 parsec away from us, to the center of the Milky Way and beyond. And you see the more metal poor the distribution of stars, the more it's concentrated on the center of the Milky Way. And the more metal rich it becomes, the orbits grow wider. Okay, so the left-hand side, that is the protogalaxy. And then there is something like a transition between this area, which is very sharp in metallicity. Something had happened to our disk, where something like a disk came up. It's not the perfect disk we see today, that would sit here, well above here, but it's something which has become a lot more disk-like. And that you see only, and it's the very same plot, just now split into high alpha and low alpha, that you kind of almost see in the high alpha, which is the stars which were born from the original gas before it was enriched by iron. So in this respect, it's the old gas which produced it. And then you see this structure over there, that is also still high alpha, still the stars from the old gas reservoir that sit up there. So now I want to convince you, what I said is there is this relatively thin, very old disk that you can no longer see. Obviously, because it has, by the merger, it has been disturbed, that does no longer exist. But I want to show you the disturbed orbit, and that you really can see, or you kind of prove this by stars which are in between these two. That is stars which are not in the disk, in the big disk we see. That is not what is in the protogalaxy, but which is in the head. And these are the stars which were kicked out from the disk by the merger and spat into the halo. And indeed, that is also where the orbits tell us where these stars are. It's not just from this plot here, additional information that proves this. So the most likely explanation for that is indeed that it was kicked out. In this plot here, down here, you see the remnants of the stars of that merging process. So that is the stars of the Gaia Enceladus. Why do we know? We know from the orbits, we know from the alpha or element abundances that don't fit the abundances of the Milky Way. They belong to the rest of the stream we see from the Gaia sausage. Yeah? And that is clearly visible, so we know who made all this. And finally, this very thin band here, where our sun, which is at 0, would sit here, if you would have taken it into account. That is the young disk produced from the material of the old disk combined with the gas of the merger. And from that is all the material, all the stars that are built, and that gets older and older in terms of it's more metal rich, and all the elements are just increased all the time. So this is really the newest stuff there. Why are we even more convinced that all this is right? There is, completely independent of Gaia, a lot of simulations ongoing to understand how galaxies are produced. One is a set of what they call TNG simulations. They produce Milky Way-like galaxies and hope to find simulated galaxy which will resemble what we see in our Milky Way. And indeed, in all their simulations, they found one galaxy, simulated galaxy, which has this Gaia picture here in a very similar form. Yeah? You see this photogalaxy here, you see a thicker disk here, and the thin disk over there. And this is very amazing in the following respect. The Milky Way is kind of an atypical galaxy because it has been, a lot of star formation had happened in the very early phase of the Milky Way. So the Milky Way has a very thick, very massive disk compared to other disk-like galaxies of the same mass. So our galaxy is a bit special in this respect. It has more massive disks than others, and it has this fantastic, huge merger in the past. And that is exactly what happened to this simulated disk. It had a very increased, very massive star formation rate in the early phase. It had a massive merger just from the simulation, and it produced exactly kind of the same features we see in our Milky Way. And that was the only simulated disk which had this combination of ingredients to make it. Until 1/4 past? Wonderful. Milky Way done. That's another topic to discuss. Black holes. I mean, for obvious reasons, black holes are very interesting. Gaia had promised to find black holes, quite a number of them. How many is to be seen, but how do we detect black holes with Gaia? Not because we can see them, but we can see a companion in a double star with a black hole, because that companion then just moves like it would be in a double star, but we can't see any companion. And if then that companion is too massive for a normal star, it's a clear indicator, or for a neutron star, or for whatever, then it's a clear indication that we may have found a black hole. So we produce within the Gaia consortium a lot of double stars, just double star solutions, and we just do it whenever we see that the normal solution, which assumes that a star is a single star, obviously looks fishy. Yeah? Then we try a double star solution to see whether it is a double star or just data is bad. And within that validation activity, a group that is specifically looking at black holes found a few examples, and one very interesting one, which is rather heavy. It's a stellar mass black hole in 560 parsec distance, so kind of, you just open the door outside and it's there, really seen. And it's very heavy, 33 solar masses, which is quite a monster for a stellar black hole. That is the data we put in. These black dots here are the individual observations. The red curve is if we assume that this is a single star, and obviously it fits a lot less than if we allow it to be a member of a double star. Again, that is the companion we see, not the black hole. Yeah, and if we then just produce an orbit solution, although we have not yet covered what usually people doing binary solutions don't like at all, although we have not yet covered the whole orbit, I think you easily see that this model is by far better than assuming it's a single star with some problems. It's further supported that this is just astrometry. And here you again see the orbit, and that would be, or is then, the orbit of the black hole. It's so much smaller because it's so more massive. That star we do see has about 0.8 solar masses, and that's 33. That is why the difference in the orbit size is so big. But you also see from spectroscopy that this really is a double star. It's a rather tight one. I just put in here our solar system. Well, then it's not with us, but far away still. Here it wouldn't be good. And it's very special in the following respect. As I said, we don't expect, or we had not expected, to have solar mass black holes which are so heavy, so massive. A theory is that that's not possible. 10, maybe 20, but not more. And then we are not the first one detecting such a massive black hole. The first ones were detected by gravitational waves, by LIGO and Virgo, but they found it in distant galaxies, just from their merging, and the gravitational waves produced by the merging of such stellar black holes. They have been in this mass regime already, but this is the very first one we found in our Milky Way. And then people started thinking about how can they come along? How do they come to life? How can they be so massive? And the idea behind that is that can only happen if they are extremely metal poor. Only then physics of the stars allow them to be so massive when they explode. Okay, so we checked, is there any chance from the Gaia data to prove that this black hole has originated from a very metal poor star? Well, there's a black hole, you all know, that is very difficult. It does not tell us any longer where it was made from. But there is a companion, because it's a double star. And this companion is extremely metal poor. The problem with that is, the companion is metal poor, but this double system has not evolved together. So the black hole and these came together later on. So why do we still know that the black hole most probably has originated from a metal-poor progenitor? Because capturing a second star is nothing which happens usually. It's not that a star flies by and another sun or black hole or whatever just captures it. That can only happen in extremely dense areas where there is many double star systems, or at least one which then, via exchange, captures the incoming one. And we know where this black hole comes from, because we have astrometry, and the full astrometry. We also know where it came from. And indeed, it came from a very dense area of a substructure of the Milky Way that we can really trace back from the observations we have. And so it's very likely that it has been born in the area where its nowadays companion also has been born, so in an area where the stars are metal poor. Most of this are already discussed. What also makes this one a very interesting one is that it's so close, which means that even from you can do a lot of observations to further classify this object and understand it better. That is why we were given exceptionally the chance to publish this, because usually the Gaia consortium is not allowed to publish any science, but just the data. But this we didn't want to hide for 2 more years. It's interesting enough, at least this single one. We have more in the queue, but this one we can publish. In principle, I would be done with my presentation, but if you are not too exhausted, I have something more which is not science, but which gives you a little insight in what the people who are doing the data reduction have to fight against every day. I leave it up to you if you say, oh, come on, not even more. I'm happy to close my presentation here, and I'm ready for answering your questions, as I just present for another 5 minutes or so. Okay. Okay. Where I kind of started with is the angular separation of this one if it would lie on the moon. That is of the order of 20 microarcseconds. That is 10 to the minus 10 radians, so quite little angular distance. And Gaia itself, the torus in which everything is, the instruments are just put in, that is a 3 meter diameter cylinder, which just covers all this. And on 3 meters, these 20 microarcseconds belong to also 0.3 nanometers, which is a silicon atom of this 3 meter. So what I really want to tell you, if you want to have this accuracy, you must make sure that you know what's happening on Gaia on that level, on the level of silicon atoms, diameters. And if you don't calibrate our instrument on that level, and if Gaia is not really stable on that level, we have to do quite something. Okay, so what we really want Gaia to be, what it was aimed to be designed for, it must not rattle, shake, vibrate, but it must rotate extremely smoothly. Because if it does not, it seems that we are looking, don't realize, we believe we are looking in this direction, but we are looking slightly apart of it, and this just creates noise in our data reduction. And then, of course, compared to that level, we have a lot of disturbance. We have solar winds, eruptions, the solar radiation pressure, which changes all the time because it's an elliptical orbit of the Gaia satellite. The thrusters, which keep it rotating all the time, produce noise because they are not permanently firing, but only when they need to fire in order to keep the instrument in the times between as smooth as possible. And we, of course, have hits of micrometeors which are there. So we expected quite something. How can we see how smoothly Gaia is rotating? Well, in principle, we could just believe what the Mission Operations Center tells us, but this is far not precise enough. So we do this again ourselves from the Gaia data. So we observe a star here, and then 4.5 seconds later we observe it here. And because we have calibrated our whole focal plane, and we know what the distance is in angular measures, we know how long it should have taken to rotate, and then we observe how long it takes, and then we see deviations. And these deviations we just plotted, and we saw very early on into the mission, that is a nice plot we discussed, a few people of us, in 2014 already. Well, what we expected is something very smooth on 0. It's on 0, that's good. But, well, smooth? Yeah. Not really. Okay, at that time we thought, okay, not good, but at least we have detected something interesting. This happens very often. Very often. We have millions of those over the whole mission. So we thought at the very early point, oh, well, okay, not good, but at least we have detected something. There's a lot of more micrometeorites and L2 where Gaia is operating than we ever thought. Let's do a paper. Good that we not did so. We started thinking about after some time, because some of these deviations we could predict. We could tell when they happen. And that should not be this micrometeorite. So we started looking into different models, what it could be. And there were two which were rather simple to compute what they should look like. One is that just the Gaia satellite just jumps and does not change the rotation. It just changes the phase abruptly. That can happen because of thermally induced disturbances. And the second thing, that is what we call microclanks. And then the second idea was it's really hit by a body, which also adds angular momentum, which changes not just the phase, but really both the orientation of the satellite and its angular momentum. And we just computed what should look like how. And let's start with the very first one, is clanks. So we just have a phase jump, and then we just can compute, because we know how Gaia is operated, that it should have this shape here. Yeah? Almost a triangle with a little plateau here. we could compute how long this plateau is, how long the increase is, that it must be extremely steep, and that is what we found. Yeah, you can very clearly see this, very steep plateau and down. So we know it's not a hit, it's thermal relaxation of the instrument, and that we have detected more than 7 million times meanwhile in the data, and we have to calibrate it out to see it. Is there no micrometeorites? Of course there are, but they look very differently. Yeah, that is the old idea, if it was just be a clank, but in reality it's something like which goes up like a parabola and then again levels off, and then the orbit control system reacts. So here, up there, it's looking different because the orbit system of the satellite changes. Is that everything we have to take out? No. What we still see is, now that the tanks get empty, there is little bubbles of fuel in the tanks, of a few gram. And they bounce occasionally against the tank wall. And by this, in a more relaxed way, they also transport angular momentum and create these waves here in our rays, which we also have to calibrate out. So this is just one example of the many things we have to take into account, otherwise the results of our products would not be as good as I believe they really are. And with that, I stop my presentation. Thank you for your attention, for your interest in the project, for being here, and I'm happy to answer your questions.
Thank you very much, Richard.
Welcome.
Please.
Gaia had some unexpected outgassing which made problems. Is this solved now, or known what it was?
Yes and no. We know what it was, and we know rather quickly what it was. It was water ice settling on the mirrors. It became immediately clear after a few days already. That is not a surprise that space missions take water with them when they are launched. I mean, they start on the Earth. There's a lot of material they take with them. But usually, well, no, not usually, they are all outgassed. And before they start operations, they are outgassed so that all the gas that they take with them is gone. That was also done with Gaia, and it didn't happen. And this was really a bad surprise because we saw that within a few days, every few days, the magnitude to which we could observe stars was halved, which was really dramatic. So we really thought we would lose Gaia at that time. But these people which operate satellites are very relaxed in these things. They're very concentrated. They heated Gaia. There's mechanisms to do so. This was gone. And then we thought, the outgassing, the heating of Gaia in the early times did not work properly. Now it's done, and then it came back, and it came back several times. We have, and that is the no, we have no idea where that gas came from. Ice. We have no idea. We know that it's there because it exactly disappeared at the temperature when ice is just evaporated. We meanwhile, after a few heating campaigns, got rid of it. It's not appearing again, so we really got rid of it. But we have no idea where it really was. And that really caused quite some disturbance, because you can imagine, I mean, final parts of my presentation, we want to have a stable Gaia, and when we heat it, it's far from being stable. It took a lot of time to again cool down to the level where it's really, really relaxed and stable. We had to do it several times. We lost a few months, but on the other hand, a few months of excellent data. It's a few weeks where we couldn't do anything at all. But on the other hand, Gaia was at the end planned to operate 5 years, maybe 6. And in July this year, we have 10 years. So I think we got it back.
Questions, please. Andrea.
You didn't mention exoplanets in your presentation.
I know, I did mention so many things, 11,500 papers, and I just discussed 4. So we could stay here for another few months, and then I would do. Yes. Exoplanets will be part of Gaia databases. When you want to have them in, you need enough data. And the first two releases didn't allow for this at all, and the third one was just the first, let's say, trial run for the group doing so. That is why they are not really in DR3, but in DR4 there will be, yes. There will be a lot of...
What do we expect to see? What is the limit of what?
I'm afraid you have to wait until these things are published. Because everybody would like to know his most interested feature from DR4, and we don't want to preempt these things before ESA public relations have really made most use of that. So they will come. Sorry, these things I can't answer.
Andrea's strongly involved in the CHEOPS mission, so she's very familiar with data policies.
Yeah. Not always a nice thing, I know, but it's probably, well, we want to have good public relations and outreach with Gaia, and if you preempt everything, it becomes difficult. Sorry.
In the back.
Do you have some onboard calibration procedures and businesses?
Well, what we do have for Gaia is onboard procedures which gives us specific data which we then use on ground to do the calibrations. That is what the onboard calibration procedures are. There's nothing we do on board directly, so that an activity is executed on board, and as the outcome of that, we would know specific calibration parameters. That is by far too demanding for what's going on board, what we have to do on ground. One example, to do good calibrations for astrometry for DR4 took us 2 years of a whole group, of a large group, to really think about that. That is nothing which comes easy. And we want to really nail it down to the best possible level. And for that we have to use kind of all the data, at least all the good data. Yeah, and that is nothing what computers on board could do. That is big computer centers on ground which are busy for months to allow for these calibrations. That is nothing which is done on board. On board is only specific calibration activities which gives us, on top of the normal science data, additional data to support that calibrations on ground.
Yes.
Yeah, so two questions actually. First, I mean, you said at the beginning that you need to correct for the position of the planet in the solar system, relativity. So
it's not kind in the beginning. It comes in one global adjustment process. Everything is done together. Yes.
So, do you think you guys can inform about the search of the elusive planet 9?
You can search about
search of the elusive planet 9. Yeah.
If planet 9 really exists, I don't think it's very massive. Otherwise, we would already have seen it. So it will be a small one, which means that the disturbance, because it's far out and it's not massive, I don't think it would exist. But this was only one of two.
The second question was about the HR diagram for what dwarf you showed. There was an interesting kind of trail at the bottom left, and maybe low significance, but
the big one or just the white dwarf one?
yeah, this one actually. The white one at the bottom left, there is a kind of trail. That's really, yeah.
This one here?
Yeah. Did people start to?
I also believe to see that. I talked to people working on that, and they, to my knowledge, have not spotted anything this one is related to. That doesn't mean it does not exist. It could also be, I mean, what really comes in here is photometry, which places the stars into the diagram. And photometry is, in some respects, a lot more difficult than astrometry is. They are more easily disturbed. Their windows are larger, so blending in dense areas is a more severe problem for them. They also get, so to speak, less light per pixel than we get. So they are suffering from a number of problems, also in terms of calibration, because there are certain subsets of stars they would like to calibrate where there's not many in. So they have to do, compared to the rest of Gaia, with a lot less observations. You have still to do a calibration, which is known to be problematic, at least in some cases. So maybe it's a photometric issue and they just placed wrongly. At least from the white dwarf people I know, I have not heard about that this is something. Yeah, but I also believe I saw something there. Yes. It's kind of, yeah. One likes to see something there, yes.
First Adrian, and then in the middle, please.
You mentioned it's one large, huge adjustment problem.
Yes.
Can you give a couple of keywords, hints, how you solve this, or how this is attacked, how the different groups in the consortium help each other, compare, solve?
For astrometry, well, okay, it's not one single, it's one single for, let's say, instrument. Astrometry, that's me who's responsible. And that is, at the end, just the least square problem to solve. So mathematically extremely easy, in principle. The problem with that is the sheer amount of data. We have to process 2.5 billion now, trillion now, in one go, plus calibration parameters and source parameters. I mean, we have, in the next release, we will have more than 2 billion sources, so it's more than 10 billion astrometric parameters for the sources, plus for the attitude, so where the satellite is looking at, plus the calibration of the instrument. So it's tons of stuff we have to put together. So it's a sheer amount, and then the whole art of these kind of data reduction is to find the right calibration model, which is a function of tons of things. And you have to do it in the right way so that there's no degeneracies in the way you set it up. One simple thing is you could just push the viewing direction of your satellite in one direction and the stars into the other direction, and they still would fit the observations you made. So you have to make sure that while you set up the calibration model, these things do not happen. That makes it really complicated thing. We have a very complex calibration model meanwhile to get closer and closer to where we want to be. Especially, that's again difficult at the bright end, because at the bright end we don't have the same instrument, kind of, and we have for the fainter sources. That is simply because at the very bright end they are so bright that they would saturate on the CCDs. And to prevent this, we just drop the signal that is already collected at some time while it travels over the CCD and start anew. But if we do so, if we throw away part of the data collected, or the light collected, and start anew with collecting light from the star, then it's essentially a new instrument. It sees a different attitude because the orientation of the satellite is just the mean value kind of about the exposure. And if the exposure is different, then the instrument is different, etc., etc. So at the bright end, we have, again, fewer sources, fewer observations. It's more problematic. So we have put a lot of effort into this. And just to give you an idea, for DR4, I believe we have spent something like 50 million CPU hours to get that solution. Finally, just the astrometry. That is really a big thing. The individual solution is not so critical. That can be done quicker, but we have to prepare ourselves and test a lot before we are finally on the safe side, or believed to be on the safe side, to really have the calibration model along to the level we want.
There was a question in the middle.
Yeah, yes, this HR diagram, so it's really extending a lot compared to Hipparcos, to the
to the cold and dim stars, go down to the brown dwarf region, I would guess. Huh? So this big difference is really this extension to the lower right. And this is thanks just to that you see fainter stars. Also, you have infrared capabilities.
Observing the optical, but at least for those which are close enough to be still seen, yeah, we still catch them. We catch everything which is brighter than 20.7 magnitude, and there's many of them. No longer many relative to what Gaia provides, but many compared to what we had. But we are going not into the infrared. The infrared may come into life with the successor of Gaia. There's the idea to have the same principle to be done with infrared detectors sometime in the future, which is called Gaia near. And then these things would see more life than we can give them with Gaia.
Also on this diagram, if you did a very high signal to noise cut on the photometry here, for instance, would you really see these features stand out more clearly without scatter around them? And can you push that to the point where you sort of identify interesting objects in gaps between these features?
There will be areas in the HR diagram this is possible. That is taken from year 2, so year 3. It's also a matter of how these things are built. I mean, you have to do the right cut, and the cut must really fit to the specific area of the HR diagram you want to really show. I just took this because I had it easily at hand. But what you very clearly see, if you have, let's say, some open clusters of stars in the Milky Way. They are all born at the very same time, and so their diagram is a little different. You know? There's not the old spread of ages. The old spread developed at the same time, and then just depending on the mass, they go into the giant phase, and you can these things so clearly. These sequences are so tight compared. You really can pick up Hubble stars and individual stars of certain, you see it even, let's say, you see this overdensity here, for example. That is also a certain point in time in the evolution of stars where they are just stuck to that area. Stuck means that they spend more time, and this means that there are more sources in this area. And so you can see tons of these things. To what extent it really, at the end, will be possible will depend on where photometry really will be. But this is not the end of the story. And maybe just to highlight this again, we had 3 data releases, but these are intermediate data releases. And intermediate in many respects. The next one will be 60 times bigger than the one we have now in amount of data. There will be 50 new data products not published so far. And of course, it will be more accurate. This is, again, not the final one. So there's tons of work still to be done. This is all very preliminary from what we finally want to reach. There's a lot of potential to improve things, and yes, many things will become visible, which people before the Gaia area had not hoped to see in their lifetime. They, at the end, will.
Thank you. General question. You know about dark matter, and now we have much more stars. Do you have an idea of how these people work now? Do they have a more accurate idea of what they want to search for or what they want to prove? Do they have a closer idea or
yes.
What happens about dark
I
matter?
think, for example, what could be done, we have outside the main disk of the Milky Way, we have these substructures, these disrupted flows of originally dwarf galaxies, let's say. So they have streams, of stars, and those we can observe. And one idea, for example, is that dark matter is not only more or less centrally but isotopically placed on the Milky Way, but that there are larger dark matter bodies which fly in the halo of the Milky Way. If they do so, they could come close to these streams of stars, and if they do so, they would disturb some stars more heavily in the streams of these stars, and would produce some deviations from which we could compute how massive a dark matter clump, if it would exist, would have been. So exactly for these things we are looking in the consortium, whether in these streams there are atypical movements of stars, although they all should go in the same direction because they have been born from the very same dwarf galaxy in the past. And these things we are looking at. And indeed we found at least one example I'm aware of where we could explain this by dark matter clump in the Milky Way, which has closely passed that stream of stars. Of course, that is rather difficult. I mean, that is one explanation. Surely there could be others which also could produce kind of the same features in that stream. That is still preliminary. But we are in a lucky situation with all the precise data of Gaia and the many stars we see, that we see many of these streams. And if these dark matter clumps would be a more typical thing in our galaxy and in other galaxies then also, we should see these more often than just once. So that is something we have to wait for, but people are looking into this. What is also possible from another thing in Gaia Dia 2 already, they looked into how the rotation curve of the large Magellanic Cloud really looks like. So they have spotted or separated, distinguished individual stars in the Large Magellanic Cloud with Gaia, and could see, even with a few years of data, the rotation curve of the Large Magellanic Cloud. And if you from that derive the potential of the mass distribution in the Magellanic Cloud, you see it does not match the light distribution of stars in the Magellanic Cloud. So from that you also can get an idea of what dark matter does. These kind of things do happen and are being done.
Many questions.
Seems so.
On one of your first slides, you showed the parallax spiral feature. You explained to us the overall velocity field, and then the
This one?
no, previously actually, just the very schematic. The fact that the parallax loops are not closed, but
yes.
they move on.
Yep. This one?
Yeah, here I was wondering, so I mean, the distance you initially infer, or where the star is at each point, determines how you sample the overall velocity field, right, with those vectors. So is there a sort of a back and forth iteration to get to the actual distance, given how you factor in the whole movement of everything going on?
Yes and no. Imagine we would have less data and we could do it in one go with a direct solver. Just put everything in a least square ansatz into one system and just solve it in one go. Then what you would see is that on the long run, they just move in this direction, so this is a proper motion, and then they have some noise around that overall direction, and half of, so to speak, I can just take this, for example, as my reference point, and try to fit in one go. What is the next one which would fit, because that is on one elliptical orbit of that. Yeah, so once I have the proper motion, I just can put all of them back in time relative to my reference point, then I see the ellipse, and from the ellipse I have the large diameter, and that is the parallax. So I could do this in one go if I would have fewer data, lot fewer data. So it's not that I have to iterate about this. but we have to iterate, but not because we can't do it in one go. There's so much data that we have to split things. We do a source update, assuming a given calibration and a given attitude of the satellite. And with this updated source parameter, then we update the calibration, having the source parameters fixed and the attitude fixed. And then we take the attitude, this fixed calibration and fixed source parameter. And this way we iterate. Because there we can just formulate it in a way that it fits into nowadays computers, big computer. And we couldn't do it in one go because it's just 2 billion sources and 2 trillion observations is just by far too much. So iterations come in, but just because of the sheer size of the problem, it's not needed. It would be smaller, and we have solved smaller problems. So the group I was working in and starting with Gaia was a so-called first look, which just checks on a daily basis whether Gaia is fine and the data is fine. And on a daily basis, the data is so little, it's still but it fits into modern big computers that just directly solves the whole problem.
Does the proper movement of the sun help in getting a larger base for measuring the parallax?
Because it's orbiting the sun, you mean?
Because the sun is orbiting around the Milky Way or moving somehow.
No, for the parallax you only need, so to speak, the orbit of the Earth. And that we could take a bigger orbit. We could have a satellite which moves with Jupiter or so. Then we could even do better. But on the other hand, then data taking would take a lot longer. So with any you see the ellipse, with Jupiter it would take years to see one ellipse. And of course we want to see many ellipses for each star to nail down with all the noise which is automatically in all the data to really nail it down to the level of accuracy and the position we want to have. So the Earth is kind of a natural thing. It's already huge. It's million kilometers, but within a year we can do something. But that the Earth with the Sun is now orbiting the Milky Way, etc., that there's additional movements of all the system, that of course we take out at the end, but this does not disturb in getting parallaxes well done.
You were speaking that you have some empty tanks.
Yes.
Tells
Yeah,
you
not,
that
not really
empty tanks.
Yeah, right, yes.
So what is the perspective? It's the lifetime of the mission?
The predicted end of lifetime, because we run out of fuel for Gaia being able to rotate in 6 hours precisely, that is for mid-February next year. At the end, they want to do some tests with Gaia, not scientific tests, but there's a few things we never found out, we never got to the bottom to. One problem is that you not only see these micro clangs and micro bubbles and micro meteorite hits, we also see that the whole instrument is kind of breathing. So the angular distance between the two viewing directions should have been a lot more stable than it really is. They violate the requirements by a factor of 250, and we have to calibrate this also out. The nice thing is that it's not what it should have been, but it's super stable. So on one revolution to the next one, every 6 hours it's getting closer and increasing, but it's super stable, and we can calibrate almost all of it away. Otherwise we're still trying to get to the very bottom of the rest. I'm talking too much. Where did I start? What was? Yeah. And these tests, we still have, over the years, got a few ideas where this disturbance, which lets the instrument breathe and change the angular distance between the viewing directions, we still have a few ideas. And that at the end we would like to test. It will not help us in our data reduction, because when this data then finally is just processed and we understand where it comes from, we anyway have to had done our final processing of the astrometric data. But it might help a lot for future missions. Something did not work like we wanted it to work, and maybe we understand why, and with successor of Gaia sometime in the future, we can do better. Not bother with that problem. So most likely the end of Gaia operations, as it looks like now, will be mid-January next year. So a few months left, but a few years to get all of this finally sorted out and processed finally. So final catalog, as I said, 2030 or maybe before.
I think with these words, we thank Michael very much again. Thank you very much.